and then 1 upon 3 factorial h cube f triple x plus 3h square k f x x y plus 3h k square f x y y plus k cube f y y, all at the point AB. So in this way I can give the Taylor series for the two variable, right? For the one variable we have already discussed the Taylor series. For the two variable we need to use the partial derivative, while and for the one variable we have, which we have already discussed in the above chapters, that we need the normal derivative to find the Taylor series. Here there are two variables, so we will use the partial derivative with respect to x for the first derivatives, 2 times derivative for the second derivatives. For example, 2 times derivative of partial derivative of f with respect to x, with respect to x, and with respect to y, with respect to y and y. So we have to use here partial derivatives for the Taylor series for two variables, right? So please note down the Taylor series for two variables. And also note that here function x, y and its partial derivatives throughout continuous and throughout continuous in an region R centered at a point AB. So all the derivatives are need to be continuous in the region. Taylor series formula for f of x y at the origin. If I take 0 0, okay, at the origin, then the Taylor series can be explained as shown in the here, as shown here. Fxy is equal to f of 0 0 plus x fx plus y fy at the point 0 0. Note that here all the values of f or partial derivative of x, partial derivative of f with respect to x or with respect to y, all are at the point 0 0. So f of xy is equal to f of 0 0 plus x fx plus y fy at the point 0 0 plus 1 upon 2 factorial x square f xx plus 2xy f xy plus y square f y at the point 0 0. In the same way for the 1 upon 3 factorial and the third derivatives, and same up for the nth derivatives. Okay, so this is the Taylor formula for f of xy at the origin. So please note this is well. This is the Taylor formula at the for the two variables at the point 0 0, or we can say that at the origin. Okay, now our last topic of today is partial derivative with constrained variables. Normally we know how to get the partial derivative of any variable with respect to any variable, right? But if there are some constraint, some conditions following which we need to find the partial derivative, then we have to follow in this way. Just look at this figure. Here P is the constraint to lie on the paraboloid z is equal to x square plus y square. The value of the partial derivative of w, x square plus y square plus z square with respect to x at P, which is depends on the direction of motion. Okay, as x changes with y is equal to 0, P moves up or down the surface on the parabola z is equal to x square, right? So this is and in the xz plane with del w by del x is equal to 2x plus 4x cube. As x changes with z is equal to 1, then del w by del x is equal to 0. That means here we need to find del w by del x with there is some constraint which we need to follow to find a partial derivative. And to understand very carefully, let us look at this, that how to find the partial derivatives of variable in w is equal to f of x y z are constrained by another equation. So this is the very useful slide that we need to, when we need to find the partial derivative when the variable is constrained by another equation. As we saw in example number 1, a typical routine for finding del w by del x when the variables in the function w f of x y z are related by another equation has 3 steps. We will follow the following 3 steps, and we will show that how to find del w by del x, del w by del y, and del w by del z, all the same methods for del w by del y and del w by del z. First step, decide which variable are to be dependent and which are to be independent. First we need to clear that which are independent variables and which are dependent variable, and if there are some dependent variable, we need to clear that this is the dependent variable, this is independent variable, then we can move forward for finding the partial derivatives. Okay. In practice, we can say that the decision is based on the physical or theoretical context of our work, which is depends on the especially depends on the problem, right? In the exercises at the end of this section, we say which variable are which. Second step, eliminate the other dependent variables in the expression for w. In first step, we will decide that in w which are the independent variable and which are the dependent variable, and then in the second step we will eliminate the dependent variable using some calculations from w, and then in step number 3 we will differentiate, as usually we are differentiate partial derivative of w with respect to x or with respect to y or with respect to z. So these are the steps that how to find the partial derivative of any variable when it is constrained by another equation. So again I remember all of you that first if we want to find the del w by del x, for example, then first we need to clear that in w is equal to f of x y z which variables are dependent and which are independent. Okay, first step. In second step, I have to eliminate the dependent variable from the expression of w, and when we eliminate this dependent variable, then after we can differentiate w with respect to partially with respect to x, usually what we are doing in the partial derivative. So by this method we can find the partial derivative when the subject to the constraint. If you want to note down, then note down these 3 steps which are very useful. Now just look at the example. For example, find del w by del x at the point xyz is equal to 2 minus 1 minus 1 if w is equal to x square plus y square plus z square, and we have the condition z cube minus xy plus yz plus y cube is equal to 1, and x and y are the independent variable given to us. That means x and y are independent and z is dependent variable. So as per our steps, first we need to determine which are the dependent and independent variables. So it is clearly given to us that x and y are x and y are independent variables, and so z is dependent variable. So first we need to eliminate z from w using the condition given. We have condition that z cube minus xy plus yz plus y cube is equal to 1. So using this condition we will eliminate the z from the expression of w. If we look at the slide, it is not convenient to eliminate z in the expression for w. We therefore differentiate both equation implicitly with respect to x, treating x and y as independent variables and w and z as dependent variables. This gives us del w by del x is equal to 2x. Y is independent variable, so partial derivative with respect to s is 0, so del w by del x is equal to 2x plus 2z into del z by del x, and for the condition 3z squared del z by del x minus y plus y into del z by del x plus 0 is equal to 0. This equation may now be combined to express del w by del x in terms of x, y and z. We solve equation 4 for del z by del x to get, if we solve this equation we will get del z by del x is equal to y upon y plus 3z square, and substitute into equation number 3 we will get del w by del x is equal to 2x plus 2yz upon y plus 3z square. Note that as per step we just eliminate the dependent variable from the expression of y, but in this case we cannot easily eliminate z from w, so we are going for as per alternate method, not alternate method but the easier method, that first we differentiate both the w and the condition partially with respect to x, so we'll get del w by del x, and from the second del z by del x. In the first equation number 3 we will get the step of del z by del x, and the number 4 we will get the step in del z by del x, and from the equation number 4 we can easily get the del z by del x in the terms of y and z. And if we put this value of del z by del x in equation number 3 we will get del w by del x is equal to 2x plus 2z into del z by del x mean 2yz upon y plus 3z square. So in this way we can find the partial derivative of w with respect to x. Del w by del x is equal to 2x plus 2yz upon y plus 3z square. Okay, so this is our partial derivative of w with respect to x, and we have asked that we need to find this partial derivative at the point 2 minus 1 1. So if we put 2 minus 1 1, then del w by del x at 2 minus 1 1 is equal to, by the calculating we will get del w by del x at 2 minus 1 1 is equal to 3. So in this way we can find the partial derivatives subject to the constraint. Okay, so this is it for today. And so what we have today discussed, we have discussed about the maximum and minimum value of the function, absolute maximum, absolute minimum, local maximum and local minimum, and the second derivative test to solve this kind of example. Then we have taken some example of partial for the maxima and minima. After that we have seen the Lagrange multiplier method. Then we discussed about the Taylor series for two variable which we can find using the partial derivative, and in last we have seen the partial derivative with constraint variable. So this is it for today. So thank you very much for listening me, and please not all the formulas which I have which we have discussed today, especially the second derivative test and the Lagrange multiplier method, and the steps to find the partial derivative with constraint variables, and try to solve some other examples as yourself using these methods, which is very useful for you in the examination as well. So thank you very much for listening me for this time. We will meet also we will meet for other topics of mathematics in future. So thank you very much. Thank you.